so let's do another example here. Let's consider that we've got a string and we've got a mass on the end of it. And let's say the length of the string is 25 centimeters. And let's say the mass is going to be 75 grams. And now I'm going to put a charge onto that mass. And I'm going to say that the charge is going to be something. Okay, I'm not going to tell you what the charge is. But I'm going to have two identical such things, both of them hanging from a point. Now, if they got the same charge on them, they're going to repel each other. And so that means they're going to be like this. And I'm going to say the angle between the two is going to be 24 degrees. Okay, so given this, I want to know what is that charge. Okay, so we've got these two identical masses hanging on an identical length string with identical charge on them. Making it all identical makes the math easy. All right, so that means that if we look at this, okay, what's going on here? Free body diagram. You did free body diagrams in Physics 1. So, free body diagram, we've got tension pulling at an angle there. Now, if this is 24 degrees, that's going to be an angle of 12 degrees from vertical. We have mg pulling down, but these two repel each other, so there's going to be some force F sub E pushing against like that. Okay, and so now these are going to be some distance r away from each other. And so we want to find out, well, what's that distance r? Because that's going to be related to F sub E. Okay, so we look at the free body diagram on the right. We know that force up has to equal force down, and force left has to equal force right, because this is an equilibrium. Okay, you learned about equilibrium in Physics 1. So again, this is basically a Physics 1 problem, because you saw something very similar to this. You saw something very similar to this in Physics 1, I'm certain, okay, when you were dealing with equilibrium conditions, and you had to solve for F sub E. So we can do the same thing. We solve for F sub E. So using the equilibrium condition here, then what we've got is, we know that force up and force down, force left equals force right. So force up is going to be T cosine 12 degrees. So that's the vertical component there. That's going to balance the force down, which is mg. Okay. Force left is T sine 12 degrees, and that's going to equal F sub E. Okay. Well, if we take the second equation and divide by the first equation, T sine 12 degrees divided by T cosine 12 degrees, then that's going to be F sub E divided by mg. So the T's cancel, so tangent 12 degrees equals F sub E over mg. Okay, so how does that help? Well, we know, once again, we've got our masses here. Okay, 24 degrees, that's some length L, that's R. Okay, if the masses have the same charge, that means that the electric force is going to repel. The electric force is going to be K, Q1, Q2. They're the same. So Q1 equals Q2. So that's Q squared over R squared. Okay. So if I plug that into the equation that I had before, okay, then that would tell me that tangent of 12 degrees, okay, is going to equal K sub E Q squared over R squared divided by mg. Okay, and so we just do algebra, and we find that Q is equal to R times the square root of mg tangent 12 degrees divided by K sub E. So all we have to do is find R. Well, we know that length is L, and that half of that is 12 degrees. So this distance D at the very end of the triangle, D is going to be L sine 12 degrees. Again, this is physics 1 stuff here. Okay, and so R is just going to be 2 times D. Okay, so that'd be 2 times L sine 12 degrees. So that's going to be 2 times 25 centimeters, that's 0.25 meters, times sine 12 degrees. So R comes out to be 0.104 meters. So now we just plug that in. Okay, so Q was going to be equal to R square root of mg tangent 12 degrees divided by k sub b. So Q is going to be equal to 0.104 meters square root of m 0.075 kilograms, because I said it was 75 grams, and times 9.81 meter per second squared, that's G, times tangent of 12 degrees. We know that K sub E is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. And so if you work all that out, now again, this is where it's very important. This is where it's vitally important that you keep track of your units. When I teach Physics 1, I try to insist on people keeping track of the units. Because if you had forgotten to convert grams to kilograms, this would not work out. Because look at what's underneath the square root. Underneath the square root, we have kilograms times meter divided by second squared divided by Newton meter squared per Coulomb squared. That meter cancels one of those meters right there. So well, actually, you don't even need to worry about doing that. Don't even have to cancel that right there. Okay, because a kilogram meter per second squared is a Newton, so that cancels, so this becomes Coulomb squared over meter squared. When you take the square root, that's going to be Coulomb per meter. That meter cancels the meter out in front, and so the answer comes up to be just coulombs. Okay, go ahead and take the extra few steps to figure that out, because that will keep you from making a mistake. If the units do not work out, I tell my students, very first, part of Physics 1, if the units do not work, there's 100% chance that you did something wrong in the problem. Don't just write down the units at the end. Keep track of the units at every step, and that way you can figure out if you're making a mistake and fix it before you get to the end. All right, so we plug in all the numbers, and what we get is 0.43, well, actually what we get is 4.36 times 10 to the minus 7 coulombs, and that's going to be equal to 0.36 microcoulombs, if you want to write it other than scientific notation. Now, one more thing. Square root has two roots, a plus and a minus. Because if they're both positive, they repel. If they're both negative, they repel. So the actual answer should be plus or minus of 0.436 microcoulombs.